In the previous video, we have seen a version of the element constraint in 2 dimensions. In this video, we will see the version of the constraint just for 1 dimension. But instead of using a hybrid consistency, we will use the real domain consistency for that constraint. Let's first make sure that we are on the same page on the signature of the constraint. So this constraint is about this expression. So we have an array of t, of integers, indexed by some variable y, and we want the result to be equal to some variable z. So let's take one example here. So let's assume that this is the content of the array t. And so if you would index this array with a variable y equal to 1, for instance, that would be in this index. Okay, so at that entry, the value of t is 4, and therefore the value z should be 4 in that case. So that's the domain of the variable y. That's all the possible indices, and that's the domain of the target variable. So that's the values. That's the value 3, 4, and 5 there. And what we will assume is that some values have been removed. Okay, we assume that some value have been removed from the domain of z. Let's assume that the value 3 was just lost from the domain of z. What can we do in terms of filtering there, since the value 3 is not a possible value anymore for the target variable? If it's not a value that is possible for the target variable, it means that the entries in t where the value 3 appear are not possible entries. And so the corresponding indices, so 0 and 5, would also be removed from the domain of the variable y. And so we can remove them like this. And so the filtering that I'm using there is that if for some entry I realize that this value t of I is not part of the domain of z, then I can safely remove this value I from the domain of y. This is exactly the rule that I just used to conclude that I should also remove the value 3 and the value 0 and the value 5 from the domain of the variable y. Okay, that's one rule. Okay, we are basically propagating in that direction. Okay, something was removed from the domain of z. What is the consequence of the domain of y? But what we can also do is do the reasoning in that direction. Okay, you should always try every possible directions to do the filtering when you implement the constraint. Let us now assume that some values were just removed from the domain of the variable y. So I realize now that the index 1 and 4 have just been removed from the domain of the variable y. And it means that these values there and these entries are not reachable anymore. But they were the only possible value that would possibly give a 4 for the target variable. It means that this value 4 should be removed from the domain of the variable z, the target variables, because there is no support in the possible left indices. You see that as possible index for the y, I have 2 and 3 that would give a 5, but the 4 is not possible anymore there, so I can safely remove it. So I remove it, and if I would translate the reasoning that I just did in terms of instruction, this is what I would compute. I would compute for the value v, so in our case that was the value 4, what are the number of indices left in the index variable y that would give me a v at the corresponding entry in t. And the answer there is 0 for the value 4. Okay, so the number of support is 0. And if the support is 0 for this value v, you can remove this value v from the domain of the variable z. That's not the case, for instance, for the value 5. So if you take the value, if you take the value 5 there, you see that the value 5 there is still 2 indices with this corresponding value 5 that are left. And so the support is 2. And this is why we cannot remove the value 5 from the domain of the variable z. If you apply these two filtering rules, so the first one in the first direction and this one in the other direction, you will achieve domain consistency. But there is a weakness if I apply like this, the filtering rules, is the time complexity, because there I have a kind of double for loop, and so I need to compute it for every value v in the domain of z, so my time complexity will already depend on the size of the domain of the variable z. But I also need to compute there the support for this value v, and again this is something that is proportional to, let's say, the size of t, right? Okay, so is it possible to lower a little bit the time complexity if I would need to implement this second rule? The answer is yes. I can, instead of that one, use another approach. I can compute first the set of the supports, the set of the values that are still supported, and I will compute them in the other direction by iterating over the domain of the variable in y. So for every value in the domain of y, I collect all the corresponding indices all the corresponding indices in t. So I can do that in time proportional of, let's say, t, okay, because in the worst case, the domain size of y is equal to the size of the array t. And then for each value in v, if I can find any support, okay, in the set that I just have computed in the previous step, then I can not remove this value, okay? And so this time complexity will be added there, okay? So that will be an addition there, which is the size of the domain of z, okay? So instead of a product, now I have a sum, and so this one is more efficient. This version is more efficient than the previous one.